Firstly, I had most everyone's abstract, and if you got some feedback from me about that. Overall, I think things are in good directions. Again, one piece of advice I have for everybody is in terms of researching the literature. How do you do that? Well, I guess everyone just goes to Google, right? I mean, you find that anything, or Wikipedia. And, you know, Google is pretty good these days. Google Scholar is, do you know about Google Scholar? So you can just Google things, and often if you're searching on keywords that are related to scientific papers, or just generally if they're in the academic literature, quite often you'll get at the beginning something that gives you results specifically from Google Scholar. But you can, if you want to go within however you use Google, you know, there are, for example, under more, you know, there's different choices, financial, blah, 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 you can go to Google Scholar. So that's one source, one direction, and it's not bad. But there are specific databases for searching the literature that can sometimes be more helpful or additionally helpful. So, has anyone ever used Web of Science or Web of Knowledge? Do you know about that? I recommend doing so.
Where can we do that?
So the way you do that is if you go to the UNM Libraries webpage, and you go to the Science Library, the CSEL, there is a link to the Web of Knowledge or Web of Science. I think if you click on Web of Science, it takes you to the Web of Knowledge anyway, which is a broader database for humanities as well. And there you can search on keywords as well as authors, or you can put in a search for a specific paper, and what you will find is other papers that have referenced that paper. And that's a very useful thing. If you want to be able to sort of go, you know, use a time machine, go forward in time, say, if this is a paper I found, is this an important paper? Well, one way of judging that is, has it been referenced a lot? Have others referenced it? Is there more modern work based on that? So some of the works that people have found are pretty old. Now maybe it stopped, maybe in 1980, that was the last time, you know, anything interesting on this topic has occurred. Probably not. So what I recommend you do is see what in modern times, how is these papers, or maybe you can see the citation record, maybe this was a hot topic, you know, from 88 to 97, and then it dropped off the cliff and no one ever thought about it again. So it's important when you're researching the literature to understand how the papers you find are related to the general community of papers, okay? So I'm happy to address any other specific questions you might have. Again, the goal here is to write a kind of review article. It's not to just review one paper. It's to review a subject. However we bite off that subject. And an additional thing that I'd like you to get a little practice at doing, if you haven't already done so, is formatting your paper appropriately as if you were to publish that paper. Now, these days, That's done almost always by submitting a LaTeX file, although you can, there are other templates the journals will accept depending. And if you go to the journal websites, you can download their template. And so, the style that I'd like you to use is the physical review style file, okay? And that means appropriately writing the abstracts, the PAX numbers, referencing, all this stuff that you gotta learn how to do if you wanna write a paper and submit for publication, okay? So that's another part of the exercise here of how do you prepare a publication for submission to a journal. And if you have any questions about that, I'll help you with it. All right? Does anybody have any general questions you want to discuss about that? Okay. All right, so what we're talking about now is laser cooling. And one of the important aspects of laser cooling, in order to be able to cool atoms, we rely on this dissipative force, the scattering force, which depends on scattering photons at some rate, and each photon carries momentum h bar k if we have, for example, a single laser beam. Now, one of the things we discussed last time was that the force is velocity dependent through the Doppler shift. And it's very important, so let's quickly review that and think about that again. So the Doppler shift arises because in the rest frame, of a moving atom, if it has velocity v, then the frequency of the electromagnetic field seen in the moving frame, say the atom frame, is the frequency produced in the lab frame minus k dot v, where k is the wave vector. Okay, that's the Doppler shift. So if the atom is moving counter to the laser beam, okay, then it sees a slightly bluer frequency. It sees a blue shifted frequency. If it's moving with the laser beam, it sees it at a slightly lower frequency. Familiar Doppler shift. So what that means is that for example, the scattering rate, or the saturation rate, we could say the scattering rate for a particular laser beam, if the atoms have a definite velocity v, will be centered at a different detuning. That is to say, the detuning, which is the frequency seen in the atom's frame, minus the resonance frequency, is I'll say it goes to, it's equal to the detuning in the lab frame minus k dot v. So this is the detuning in the lab frame, omega L minus omega EG. And so the scattering rate is now given by this Lorentzian function depending upon the velocity, right? So, the detuning at which we get the peak absorption depends upon, or the peak scattering depends upon the velocity. Of course, what this means, as you know, is that if I have a thermal sample, if I have, say, a vapor cell at a thermal temperature, the absorption, if I looked at the absorption as a function of frequency, it will be peaked at the resonance frequency, but the width of that resonance depends upon the spread of velocities that we have. If we have the atoms that were, if they were sitting at zero velocity, then the peak of this Lorentzian is when the detuning is zero. And when I have a spread of velocities, what that means I have a spread of different Lorentzian functions. In fact, I have a big spread depending on the thermal distribution. So if I have a thermal distribution of velocities, then I have a much bigger spread in my absorption line. And that width is called the Doppler. It's called Doppler broadening. As opposed to lifetime broadening, the natural line width, which was related to the spontaneous emission rate, or the lifetime of the sample. This depends on the temperature of the sample. And generally, if I put on a laser beam, then what we see here is that I'm not going to address all of the atoms in this Doppler line. If I scan the frequency, then I will address different atoms depending upon which atoms' velocities are close enough such that their Doppler shift makes me resonant or near resonant with that laser beam. Okay? So what we see here is that there's a kind of velocity class of atoms that are going to be close enough to, or going to be addressed by the laser beam when it's at a certain frequency. When this difference is close to zero, then I have strong absorption and strong scattering. Okay? So there is a velocity group or that is addressed by the laser beam that depends upon when this detuning is equal to I have resonance. And I could just say there's a spread of this plus or minus gamma, kind of gives me the spread of velocities. That are addressed by this laser beam. Okay, so last time I flubbed, because I was thinking about, I had two different things in my mind, and I confused the issue. So let me revisit the question of how we can then use the scattering force as a method of decelerating a thermal beam of atoms coming out of an oven. So let's just imagine we have some kind of oven that is collimating some thermal beam of atoms. Okay. Now, first of all, it doesn't make sense to draw the picture I drew last time. Let's call this the x direction. there is a distribution of velocities of atoms that come out. Of course, the atoms that I see here, I have very few at zero velocity, some peak velocity. I'll have some distribution of velocities here, whatever that distribution is, given by some Gaussian thermal distribution. Okay? So that's the distribution of velocities that are coming out of this beam. Obviously, I don't see any ones going negative. I see nothing going at zero velocity, and then there's some peak velocity. Right? We buy that? So now, I want to move as many of these atoms from their peak velocity down to lower velocities. So what should I do? Well, what I should do is push the atoms back with some laser beam. And I should, say, tune the atoms such that I have the maximum force near the peak of this distribution, right? So I should make this resonance. Let's say I should choose my detuning. This is V sub x. My detuning should be chosen such that for atoms with this velocity, I'm on resonance. This is negative here. So I should make a red detuned. So here's in the lab frame, my laser is detuned to the red. And my peak is here. My force will be in the negative. If I were to plot the force of this laser beam on these atoms when I'm detuned here, well, the force is negative, right? And as a function of velocity, when I'm at this detuning, the peak force is here. And I have some kind of Lorentzian. This is my force. What is the width of this Lorentzian as a function of velocity? Well, I mean, you can see here that the width depends on gamma, right? And the width, therefore, is going to be related to, in terms of velocity, is going to be related to gamma over k. So this width here, the spread of the forces, that is to say that there is a kind of capture velocity which goes like gamma over k. If the velocity gets too big compared to gamma, such that k times that change in velocity, that means the Doppler shift takes me out of resonance. And out of resonance is set, in this case, by the natural line length. Is that clear? So, what's going to happen in this case? Well, the atoms that are right at this peak are going to feel a strong force. The atoms that are slightly at slightly bigger velocities are also, at least if their velocity isn't so different from the peak velocity by this amount, they will also feel a force. So the faster atoms will start slowing down. Once they slow down, they get even a bigger force. Then they start slowing down more. Eventually, they get out of resonance because the force that was applied to them slowed them down so much that now they're Doppler shifted out of resonance. And so I'm going to sort of dig a hole out of here from this velocity class, and I'm going to pile them up. They can't get too far afield because they stop getting a force once they're too far out of resonance. And so I've taken a small velocity class, I've slowed them down and compressed their velocity slightly. Okay, that's the picture I should have drawn last week that I messed up. Okay, now, as we also discussed, in principle, I can do much better, and in practice as well, by moving the peak of this distribution in concert with the slowing down of the atoms. Because as they slow down, I can do one of two things. As they slow down, what that means now is that they would be in resonance if I had just moved the frequency up a little bit more, because now there's less Doppler shift, right? Because if they're at rest, or they're close to rest, I want them to be kind of right at resonance. Alternatively, I could move, if I can use some kind of Zeeman shift or other energy shift, I can move this energy down. So as long as I move this peak shift, so I can move this detuning such that as the peak energy or the peak velocity shifts, I lower this detuning, make the magnitude smaller as V decreases. Is that clear? So that means that I can do one of two things, and both are done. I can adjust the frequency and that's what's called chirp cooling. Chirp, time-dependent frequency, such that as they are descending out of this oven, they see a bluer and bluer frequency. Or alternatively, I can shift this level from very high, make it a big red detuning, so I reach the high velocities, and then lower that energy so I reach lower velocities, and I can do what's called a Zeeman slower. Both of these techniques are used as a way of sweeping this and moving many more of the atoms from many more velocity groups into lower and lower and lower velocities. Yes?
The beam or the cloud of the atoms there will have a tendency to go back into its original velocity distribution. But do you know on which time scale that happens? I mean, if laser cooling is much faster.
So the answer to that is the equilibration that I think you're referring to arises due to collisions between the atoms. The atoms that come out of these kinds of samples are vapors. They're extremely dilute. The pressure is extremely low. The density of atoms is something like 10 to the 10th. I mean, coming out of a vapor, maybe it's even less than that. But it's definitely less than 10 to the 10th atoms per cubic centimeter, which means that the atoms are essentially non-interacting particles. They're darn close, in some sense, to an ideal gas. So the thermalization scale, although that kind of thermalization is extremely important if we want to try to do evaporative cooling, which is the most important final step toward the ultimate coldest temperatures that are now obtained in laser cooling, which gets us to degenerate quantum gases, Bose-Einstein condensates, in the context of laser cooling, we forget about collisions. So the atoms do not thermalize. For all intents and purposes, they're kind of in like a thermos. They're just surrounded by, they're in a vacuum. I forgot to mention that. I can't do this just in free space because the thermal atoms from the air will kick them around. They're just at a much hotter temperature. In fact, what typically limits a lot of laser cooling is how good is your vacuum. Because if you have background hot atoms, they're just bullets flying around, going to be knocking those atoms out of the world. Yes?
So why use the laser beam causes to raise different frequencies instead of this, just adjust to the frequency?
Why not have it sort of simultaneously many frequencies to adjust that? I really don't know how that's done in terms of the most efficient way to capture as many atoms out of the cloud, out of the beam as possible. The chirp works very well. It does have many frequencies. In fact, as we're going to discuss today, and I really don't know this so well because, I'm not an experimental physicist. But I believe it is the case that the vast majority of laser cooling experiments are not done this way anyway anymore. What is done and what we'll discuss is related to a comment that Cornelius made earlier in a previous lecture about if I have a trap, why don't I just collect a low energy tail in that trap? Well, that's essentially what's done in the majority of experiments, and we'll talk about that today, or some of it today, some of it on Wednesday. What one tends to do is we have enough atoms around, and we can capture the fraction of the atoms that are in a low velocity tail that can be captured. We could try to capture more of the higher velocity ones, but to some degree it's diminishing returns because the trap can only accommodate so many atoms. It has limitations that we'll talk about in terms of depth and density. So, you could try to get more atoms in there, but you're not going to be able to do it. And you can do enough with the number of atoms that are in that low velocity tail. All right, so there's another point. So this experiments like this were done first. The pioneer experiment was done in terms of decelerating a laser beam was done by Bill Phillips in the early 80s, 1980s. And then once those atoms came out of this beam in the Zeeman slower, he loaded some of them into what was then, and is still now, but the sort of first magnetic trap. The atoms are little magnetic dipole moments, right, because they have spin. And you can create a magnetic model, which we'll talk about for trapping atoms. You can't get that many atoms into that kind of trap. It sort of depends on how deep the trap is and how cold these atoms are. Now, these atoms aren't really, in some sense, that cold because, of course, I'm slowing them down in this direction, but the atoms are heating up in the transverse directions because they're getting all these kicks. We'll talk about recoil heating today. So the temperature, in some sense, if you try to put them into, they're not equilibrated in some sense in all three directions. The temperature of the atoms that come out of its beam is not very low on the scale of laser cooling. It's just a small, I don't know, it was something like 1/10 of a Kelvin. And that's not very cold for a magnetic trap. So directions shifted or were going sort of acting at the same time, really the pioneering experimental work on really creating laser-cooled samples of large numbers of atoms that could be held and then manipulated were done by Steve Chu. Famous Steve Chu, now our energy secretary. Chu at that time was at Bell Labs. And there was this idea of Doppler cooling. Doppler cooling was an idea that was simultaneously proposed by Kenshin Shallow and Wineland and Itano in the mid-70s somewhere, maybe 75, 76, I forget. I was a very small tyke at the time. But it wasn't really done until the 80s. Why, I don't really know. Well, perhaps there was experiments by Wineland and Itano in ion traps. I'm not sure early, but as far as the neutral atom traps go, the first experiments were done on this decelerating the beam by Bill Phillips, and then the Doppler cooling was implemented in Bell Labs in Chu's group. The idea is to kind of take this picture from the accelerating frame into the lab frame. Okay? So what we want is that to be the force, the damping force, to be biggest for zero velocity atoms. And the idea is quite simple. So instead of thinking about a single laser beam, let's imagine somehow, some way, we have some atoms that are already at low velocities, low enough.
Wait, that must be backwards, right? You want the cooling force to be highest for the fast moving atoms, not this ones that already stopped.
We want the, I'm sorry, what I want is the friction to be highest at the zero. Okay. So here's the picture. The picture is quite simple. Let's just think about motion in 1D. Okay? See here the friction, I didn't mean the force, I meant the friction. The friction is highest at the peak. Here I want the friction to be highest at zero velocity. Let's take a look at that, because the friction is big right here at a high velocity. Remember, the friction is the force opposing velocity, so it's a negative slope. So let's imagine the following is true. We have laser beams that are detuned to the red. Let's make them equal in frequency. An atom which is at rest feels no force because it says equal force from both atoms, from both laser beams. If the atom has velocity to the right, and that velocity is not very big, well then it's going to be, see this laser beam slightly to the blue, and this laser beam slightly to the red. If it sees this laser beam slightly to the blue, well then what happens? It sees this one closer to resonance. And if it moves in the opposite direction, well then it sees this one slightly to the blue, and this one slightly to the red, which means that this guy shifts closer to resonance. So whichever way the atom goes, it feels a force opposing its velocity. That's a very simple and appealing idea. And that's it. That's the whole story of Doppler cooling. It gives me a damping force because now I get a force. This is what was called the friction coefficient. This alpha is not the polarizability. It's now the friction coefficient. I have friction. I want that friction to be maximum when it's at zero velocity. So the whole question now is, how does this to cool the atoms, and what temperature can I reach? So, let's look at this friction coefficient. So, well, we have the scattering force. This is the scattering force from one laser beam. Now we have two laser beams. So we can this is for the k vector in the positive direction. This is for the k vector in the negative direction. So this force is equal to h bar k gamma over 2 I over I stat. Now, before I get into this, I should mention one thing. Of course, if I have two laser beams that are counterpropagating, I have a standing wave, right? And you remember we talked about when you have a standing wave or you have a variation in the intensity as a function of position, we have not only a scattering force, but we have a dipole force, right? But we also said that the scattering force dominates over the dipole force when the detuning is small compared to gamma. When the detuning is big compared to gamma, the dipole forces dominate. That's one of the things we discussed last time. We can get bigger AC Stark shift compared to scattering rates, very far presence. So firstly, we're going to assume we're going to be looking at this close enough to resonance that the scattering force dominates, although we're going to have to think about that ultimately, whether that is really the best assumption or not. Moreover, when I have a high enough intensity that I start saturating the transition, well then stimulated processes can start dominating over spontaneous processes. And I can get stimulated redistribution and multiphoton effects. So for high intensities, this idea that I'm just going to add the two forces is totally BS. And in fact, it turns out that if you want to cool at high intensities, you should detune to the blue. You can impress all your friends by talking about blue molasses. You'll be so in the know of the most obscure thing in the world. You know. So we're not talking about blue molasses here. Impress Grant, tell him about blue molasses, see if he knows.
Shouldn't it see a lumpy force then still?
It does. There is a dipole, and that it sees. I mean, when you have,
even if you ignore the dipole, because this
you do. What you have. So this, I'll just give you a little bit of preview. These are the dress states. Not a preview, but because we're not going to talk about this, but it is a preview of sorts because it's. So if you have, suppose you have the standing waves, and I look at the dress states. Now, the point here is that there is this kind of absorption emission cycles on hills and valleys. Cohen Tanuji studied this back in the 80s and showed that if I was detuned to the blue, I can cool in this kind of cycling of the scattering off of these new dress states. Ignoring the dipole force is there too. And this is what they call Sisyphus cooling. In fact, the idea of Sisyphus cooling, which is now well known in the context of the sub-Doppler mechanism that we'll talk about, was originally discussed and understood in the context of blue molasses. So this bumpiness of the potentials was essential We'll talk about Sisyphus cooling later, but it was originally discussed in the context of blue molasses. But we get ahead of ourselves. We're not talking about blue molasses. We're talking about very basic idea of Doppler cooling, which requires red molasses. And so we're going to, again, assume we're at low saturation, because if we're at high saturation, it all doesn't make sense at all. We have to really do things more complicated that we just discussed. So I'm going to ignore saturation, assume that my saturation parameter is small.
Does the width really depend on K, like you said earlier? I was confused by that.
What do you mean? The capture
The
velocity?
capture velocity.
It does. Let's look at that. We'll look at that in a moment.
I thought that was just the width of the force in the resonance.
Let's take a look. I'll explain why it does. So we have the force of the two counterpropagating laser beams. Okay? One with K in the positive direction. This is our one direction. Okay. So let's draw what this force is as a function of velocity if the detuning is negative. Okay. So if the detuning is negative, this guy is peaked at negative velocities. And I get this force pushing it positive. In addition, I have the force pushing it in the negative direction. It's a negative force. And it's another Lorentz. Okay? So, the sum of these is whatever the heck it looks like. Is the total force. Sum of these two things. So the capture velocity depends on the detuning, right? So in some sense, where there's friction, as we see here, is that the force right at the origin is 0, and for small velocities away from the origin, it has a linear slope with a friction coefficient. The capture velocity is going to depend to some degree on how big I can make this friction coefficient. So that's going to depend on, well, the detuning, right? Because if I bring these, if I make the detuning 0, there's going to be no friction at 0. If I make the detuning too big, well, then this thing flattens out. Again, there's no friction. There's an optimal detuning. Is that clear? So let's just calculate this. Let's look at this, expand around v equals 0. So my force, its function of velocity, is to take the derivative of this with respect to velocities. And that is equal to four h bar k squared I over I sat times 2 delta over 1 plus 4 delta squared gamma squared squared times the velocity. Okay? So, from this, we see for these two counterpropagating beams, where we just added the scattering force, we have our friction coefficient. The friction coefficient is positive when the detuning is to the red. And what we see here is that the peak, you can check for yourself, the maximum friction when the detuning is a half a line width, negative to the red. So, in that sense, it is within this range that I'm going to get friction. That is, in some sense, the capture velocity range. That is the spread within this range. I see a force that opposes my velocity, and that is set. That scale is set by the line width. Okay. So we have friction. That means, in principle, we have cooling, because the what this says is that, you know, the rate of change of the momentum of these atoms, the center of mass momentum of these atoms, is equal to minus gamma v, or minus gamma over m. Oh, I think I've got some of mine. I guess that's right. Okay. Keep. So if I look at the rate of change of the kinetic energy of these particles, of these atoms, let me look at it this way. Let me back this slightly differently. Let me go back. Okay, so the rate of change of the kinetic energy of these atoms, according to this expression, 2p dt 2m, which is equal to minus gamma p squared over 2m. Yeah, okay, good. Now I can see where I'm going to this. So the effect of friction on this system is to damp the kinetic energy. We know that because the change in the energy is equal to the work done, and that work if this force is proportional to velocity, then we get the same expression again, where E is p squared over 2m, the kinetic energy. So the change in the kinetic energy of the particle is related to the work done on the particle based on the radiation pressure. And what we see here is that there is a damping rate. Yes,
What is F?
F is this force.
No, I mean, after, when you go from F to V.
No, that should not be there, sorry. F is equal to minus alpha V, pardon me. And then 1/2 mv squared is my energy, or p squared, which you want. Thanks. All right. So, according to this equation, in steady state, the kinetic energy goes to 0. Just damps to 0. That can't be right. Why not? What did we leave out? Well, what we left out, I mean, when we wrote down this equation, what we're really thinking about is the scattering force. But this scattering force, which gives rise to friction, is arising not from a continuous force, but it is arising from discrete processes. Absorption and emission of photons. In fact, this picture of motion of the atom in this light field is akin to the problem of damping in molasses, which is why this is called optical molasses. What do we mean by that? Well, let's think about the problem of damping of the motion of a particle in a fluid. If I have friction as the particle moves in a fluid, does it come exactly to 0 velocity? No. Why not? Well, because what's going on, if I think about it, here's my particle, it's moving in the fluid. But the fluid is consisted of corpuscular constituents, molecules. And the effect of damping is coming from the discrete collisions of the particles that make up the fluid, even though we treat at a microscopic level the fluid as a continuum. At the microscopic level, the fluid is made up of discrete entities. And so ultimately what happens is that the particle comes to equilibrium with the particles and the temperature in the fluid. How does that happen? Well, this is, of course, the process of Brownian motion. And so there is a great and important analogy between the process of laser cooling and the thermalization of the atoms in optical molasses and the problem of thermalization of a Brownian particle. How do we think about this? Well, one way to think about it is let's think about how the momentum changes in this particle as it moves through this fluid. There's going to be a damping, which is related to friction. in addition, there is a force which we call the Langevin force. Which is the fluctuations of the mean force. This is related, this friction is the mean effect of many collisions. But in addition, there's fluctuations around that mean due to all of the collisions that are occurring. This is a random force, and Langevin wrote this down as a so-called stochastic differential equation. Stochastic in the sense that we don't know what this force is at any time. We only know its statistical nature because it's arising from this fluid that is in some thermodynamic state. We don't know the motion of every particle in the fluid. We just know its statistical properties. What does that mean that we know its statistical properties? What that means is that I can say average over an ensemble of many particles, this fluctuation averages to 0. So that on average, I feel damping. However, there are correlations between the forces. So I can ask, what is the correlation averaged over the ensemble between the force at different times? If I assume that those statistics don't depend, are the same kind of statistics at any time, then this correlation doesn't depend upon the origin of time, but only the difference in times. So we call stationary statistics. So it's some function g as a function of the time difference with some strength, which is traditionally called 2D for reasons that we'll explain in a moment. So the fact that the force correlations, this is my correlation between these forces at different times, depends only on the time difference, is to say that my statistics are stationary. Not that things aren't changing in time, but the nature of the statistics are the same at all times. So, now if this is a random force from these molecules coming in hitting these particles at random times, there's a finite correlation time. The force at one time is related to the force at a later time over some time scale, after which everything's random and I've lost track of what the force is, because it's fluctuating. So there is a correlation time of the fluctuating force. A standard assumption we make in order to make some headway, but also one which is often an excellent assumption, is that that correlation time is extremely short compared to the time scale over which the momentum damps. So, here I am, chugging along, trying to move through this molasses, and I'm getting hit by all these particles coming at me, and they're jumping around, and I slow down as I'm going through this molasses. But the random forces are fluctuating much more rapidly than the time scale it takes me to slow down, because I'm much heavier. So there's a sense in which we think about the bath or the fluid as being a big reservoir that re-equilibrates very quickly, much faster than the time scale over which I damp. In which case we make what's called the Markov approximation. And approximate this thing, this correlation function, as a delta function. So that for all intents and purposes, there's no correlations over any time scale of interest. I take it essentially to 0. With this assumption, we can then look at the statistical properties of the motion of this particle undergoing Brownian motion. So let's look at the integration, the formal integration of that equation of motion. dp dt, so we can integrate that. That means that the momentum at some time t is the momentum at some time t0, e to the minus gamma t minus t0, plus the integral from t0 to t dt prime e to the minus gamma t minus t prime, the fluctuating force. Okay. That's just the formal integration of that differential equation. You differentiate that, you get that. So what this says is that the ensemble average of this thing, of the momentum, the mean momentum goes to 0. The most probable momentum will be 0 at long times. However, the fluctuations in momentum as a function of time, which is the average of the deviation of the momentum from its mean value. If we plug this in, we plug in this, what we get is that this is equal to the integral from t0 to t prime, dt prime, from t0 to t double prime, t double prime. We put this inside the integral.
I think the limits of the integral are t prime and t. Or the upper limits, right? Am I wrong?
Correct. That's what was wrong. Okay, so under the assumption of the Markov assumption, this correlation function is twice the diffusion coefficient times t minus t double prime. And then we can do this integral and find that the mean fluctuations in the momentum as a function of time are equal to twice the diffusion coefficient times 1 minus e to the that's the answer to that integral. Okay, so how do we interpret this? Well, let's look at these fluctuations in the momentum. For times, let's look at the limits of this expression. Let's look at this for times t minus t0 that are much bigger than the correlation time, between collisions in this Brownian motion, but much smaller than the damping time. There's plenty of time in between those things. This thing, we set this essentially to 0. Okay, but we're going to look at the time short compared to the time where it's come to equilibrium. Then we can expand this for short times, and we get that this is equal to twice the diffusion coefficient, T minus T0. This is diffusion. So the effect of these random kicks is to cause this particle not only, at least in the directions where it's not feeling the mean force, as well as the direction which feels the mean force, is to get some random kicks which causes it to diffuse. And the effect of that diffusion is to give me some, on average, 0 velocity, but not 0 fluctuations in my velocity. And those fluctuations grow linearly in time. That is the hallmark of diffusion, right? So if I have a Brownian, one of the effects of the Langevin equation is to cause diffusion. The other thing we see is a very important result if we look at this in the long time limit, when t minus t0 is much longer than the damping time, then this goes to 0, and this becomes the diffusion coefficient over the damping rate. However, we know what we expect if this particle eventually comes to equilibrium, and we're looking at this in 1D. So if I assume that my bath is at a finite temperature, then in equilibrium, averaged over the ensemble, the average p squared over 2m is given by the equipartition theorem, is 1/2 Boltzmann's constant times the temperature. Remember, the mean is 0, so the fluctuations is equal to the average of the square, right? And this is equal to the diffusion coefficient over the damping coefficient. And this relationship is extremely important. This is a fundamental relationship of statistical physics. This relationship is known as the fluctuation dissipation theorem. It says that the diffusion coefficient, which is related to fluctuation, and the damping coefficient, which is related to the damping of energy, are interrelated to one another. And I guess I left my 2m out here, p squared over 2m. So this is then equal to, the diffusion coefficient is gamma m. So this is a very fundamental result. It says the following thing. When I have damping, and that damping is due to the random collisions or discrete events of corpuscular particles, those particles have two effects. One is, on average, to cause damping or dissipation, but in addition, cause fluctuations. They have the same physical origin. That origin is the collision, so it's not crazy that the coefficients that define those two processes are interrelated to one another. And the fluctuation dissipation theorem gives it right here. So, what this tells us about laser cooling here is that the temperature that we expect to reach will be related to the diffusion coefficient divided by the damping coefficient. Mass. We have our damping coefficient, we now need to think about the diffusion coefficient. Well, why is there momentum diffusion in this problem? There's momentum diffusion because in laser cooling, momentum diffusion from random recoil in absorption and emission. Here I am, I'm an atom. I'm moving along at some velocity v. There's a laser beam that's coming at me. Now, there's going to be, in a given time interval, a random, or there is not a deterministic probability that I will absorb. I only absorb with some probability. It's dependent on quantum mechanics, right? So there is a fluctuation in absorption. In addition, once I'm in the excited state, well, there's also, I don't know in a given time interval whether I'm going to emit, and moreover, there is a question of what direction I'm going to emit into. My scattered photon doesn't come out in the same direction every time. It comes out in a random direction depending upon maybe the dipole pattern, but it typically, actually, the atoms are being emitted in, well, turns out that although we treat our atoms as a two-level system, in fact, they're really not. But that's a whole nother story. Come back to that. But all of that means that there's fluctuation in absorption and fluctuation in emission. Before we conclude today, let's just get a sense of what that fluctuation is. And from that, we will get the predicted temperature given by this balance between damping, which gives rise to cooling, and fluctuations, which give rise to heating. And the balance between them determines the equilibrium temperature that the atoms reach in optical molasses. To do that, we can simply just look at the following very simple equations, which I will cheat and look at so I don't get the signs wrong. So let's just do momentum and energy conservation and absorption. The change in momentum of the atom, it starts with some initial velocity, gets some final velocity, is related to how much it absorbed from the laser beam. And energy, it started with some kinetic energy. It was in the ground state internally. It picked up h bar omega L of photons, and then afterwards, it has a different kinetic energy, and it's in the excited stage. What this tells me then is that the absorbed frequency, this is the laser frequency, is equal to the resonance frequency plus the recoil energy in frequency units plus the Doppler shift. I am resonant when the Doppler shift matches and with a small recoil shift. In emission, I can do the same thing. I have now the difference between my final energy, what I'm going to call the primes, the energies in emission. I lose h bar k depending on the direction of the scattered photon. And my energy, I start in the excited state. I have some kinetic energy. I end in the ground state. I have a different kinetic energy. And I emit a photon. If I then look at this difference, it tells me that the emitted photon has a frequency that's equal to the resonance frequency minus the recoil plus So, what do we learn from this? What we learn is the following, and then we'll conclude. The change of the energy of the atom is equal to how much it absorbed minus how much it emitted. That energy is equal to L initial minus K So, in a scattering process, the atom's kinetic energy will change. It'll change by an amount that depends on the difference in the Doppler shifts, but it will always gain 2 recoils of energy. This is what we call recoil heating. This recoil heating is due to the random momentum diffusion that the atom is receiving due to the fact that it is scattering, it's absorbing and emitting discrete particles, the photons. Now, this is the Doppler shift on absorption. This K vector is fixed. But the K vector of the scattered photon, although it's about the same magnitude, the direction varies. In fact, if I average this, I mean, sometimes it goes this way, sometimes it goes that way, and maybe there's a dipole selection rule, but on average, the direction of the scattered photon is 0. It averages, on average, this Doppler shift on average, due to emission, when I average over many scattering events, this averages to 0. And this is the basic energy picture through which we understand how laser cooling happens. If the Doppler shift is negative, then I can, in general, I will absorb a redder photon than I emit. On average, I emit a photon whose energy is the resonance frequency with the recoil. But my absorbed photon, because I go in a certain direction, is going to be redder than the photon at average that I emit. And therefore, I lose energy if I can make this less than this. However, I can never get to zero energy because I always have diffusion and I always pick up recoil. Which means no matter what I do, no matter how clever I am, no matter what mechanisms I choose, laser cooling has a fundamental limit. And that limit is the recoil energy. And there is a temperature associated with that. Of course, we don't get to BEC from laser cooling. People tried. People tried to beat this by somehow avoiding the recoil in some kind of cooling through some kind of trick of a dark state where I'd fall in if I was just, I somehow capture those atoms that are in the very low velocity range just sort of by accident. It never worked very well. It really took us to be able to do evaporation and incorporate a new cooling mechanism to enable us to get to BEC. But laser cooling is an important first step, and we're going to finish this up next time to put in the diffusion coefficient. We see how much heating we get. We'll put in the diffusion coefficient, we'll get the Doppler limit. All right?